It has just started, and I have to warn you, it's going to end very badly. Because today we are going to dive into the heart of one of the most extreme objects found in our universe. Stars that are, in a way, this close to becoming black holes, namely neutron stars. We stand before the remnant of a vanished star, one of the strangest compact objects. They form when a star with a mass 10 to 30 times that of our Sun runs out of nuclear fuel in the core of the giant star. The energy released by the fusion of atoms is then no longer enough to counterbalance the force of gravity, which tends to make it collapse in on itself. And the outer layers of the star then plunge toward the center, powerfully compressing the core, on which they will rebound. By tearing the star apart in a cataclysmic explosion called a supernova, the core of the star itself ends up compacted into a tiny fraction of its original size. In place of the now vanished giant star, all that remains is an extremely compressed core of matter, a neutron star, which we are going to try to dive into. This sphere, with a diameter about the size of a large city, weighs between 1.4 and 3.2 times the mass of our Sun. And in this star, where matter is infinitely more compressed than in a rare mineral, we find the densest materials in the known universe. It is estimated that the volume of a small teaspoon, just a few drops of the matter making up a neutron star, has a mass equivalent to that of 100 oil tankers. As for the volume of a sugar cube of this matter, it has the mass of one of our mountains. And if this information already gives you a headache, then just imagine that, on this star, the volume of, say, an aspirin tablet weighs around 100 million tons. And just to spice up our journey to meet these tortured and compacted balls of matter, we're going to dive into a very particular and relatively common type of neutron star, which at the beginning of their lives have phenomenal rotation speeds. It's believed that these extremely bizarre objects, called pulsars, which can spin dozens of times per second on their own axis, are formed by taking on the rotational movement of the collapsing star that gave birth to them. And as seen through our telescopes, this furious rotation makes them appear to blink because their magnetic pole blazes by emitting an incredibly energetic radiation. It's tempting to think that by being as far away from such a monster as we are now, from the Sun we could see it pulsing and sweeping space with its two beams, with metronome-like regularity, disturbing the surrounding dark night like a lighthouse. Yet strangely, at such a distance from a pulsar, we would probably see only a tiny, barely visible blue dot. Because even though the surface temperature of these stars is close to 1 billion degrees just after their formation, this temperature will drop quickly. It drops below 1 million after a few thousand years of existence, and even though that's still hundreds of times higher than the surface temperature of our Sun, we have to keep in mind that the apparent brightness of a star depends on its size. So, although it's extraordinarily hot, the tiny surface area of a neutron star, compared to that of a standard star, means it emits very little visible light. Besides, even the existence of these high-energy beams emitted at the magnetic poles wouldn't be of much help for us to detect the pulsar. Because, just like the beams of light from a lamp are barely noticeable as they spread through the air, here, the intense pulsed radiation isn't visible as it travels through space. At most, could we see their reflection? When these pass through, ionizing along their path, part of the matter present in the nebula resulting from the supernova explosion. In fact, as strange as it may seem, the presence of a pulsar nearby would be visually discrete, even if one of its beams was directed at us. Again, we would most likely see almost nothing. Although spending a few minutes in this new setting would not, in conclusion, inevitably lead you to death. Because it's best to avoid being exposed to those electromagnetic radiations, poor in optical components, but terribly rich in energy in the field of radio waves, X-rays, and gamma rays. So, a pulsar is, in a way, a Death Star, constantly spinning and firing rays that can irradiate you at both ends. We have even exceptionally been able to observe bursts on some of them. Sporadic flashes that, although they last only a few microseconds, emit as much energy as 1,000 suns. In reality, to be able to clearly see this star that's still a bit too dark, we're going to have to get closer, and so inevitably die again in the process. With a taste for adventure and instant roasting, here we are now, 50,000 kilometers from the pulsar. And it's funny to think that at such a distance, which is about 1/8 the distance between the Earth and the Moon, so, with its diameter of about 20 kilometers, it wouldn't be any more visible to you than a pinhead held at arm's length, except that it shines, and not just a little. We know of so-called X-ray pulsars, whose total luminosity, across all wavelengths combined, ranges from 200 to 50,000 times that of our Sun. We've already been turned into soup and are now entering an area where it's not good to go, because we're close to the star. In addition to the extremely energetic beams of X-ray and gamma radiation passing through us from all directions, the titanic intensity of the magnetic field itself is now capable of deforming our molecular structures. Soon, like being caught in a vise, it will begin to fall apart, eventually ending up joining. The myriads of particles charged with electrons or positrons that shoot out from all directions and encircle the star along the paths of these lines of force. Perhaps you will find some small consolation in knowing that X-ray pulsars have been observed within binary systems, swallowing up to 1 trillion tons of gas from their companions every second. Some of the matter captured in this way is transformed into plasma, channeled along magnetic field lines to the star's pole, where due to the intense gravitational field, it is extraordinarily accelerated as it falls. To the point that 10 grams of this plasma soup, crashing down at nearly 100,000 kilometers per second, releases at the point of impact as much energy as about 15,000 tons of trinitrotoluene. There, over an area of barely more than 1 square kilometer, heated to 100 million degrees. This infernal rain of plasma, moving at 1/3 of the speed of light, can release as much energy as about 10,000 suns. And for us, where our life ends, another pleasure begins. Because imagining that we still have eyes left to cry. We could see, as we descend toward the surface, amazing gravitational lensing phenomena occur, distorting reality around us. Because when facing this type of star, you can actually see more than half of it at once, and thus be able, in a way, to observe what's at the back on the other side. From that point of view, landing on a neutron star is pretty much like getting as close as possible to an almost black hole. Because the intense gravitational field generated by this compact star bends the light rays around it, to the point where, ignoring the light emitted by the star, it would theoretically be possible, as you approach it, to see the night sky visually distort, the starry landscape strangely stretch, and then gradually concentrate above you into a tiny circle containing most of the celestial dome. And it is there, at the equator, in a slightly calmer area with a temperature of about 1 million degrees, that we are going to try to crash. Because, inevitably, the landing here is likely to be one of the most turbulent stages. Just think that due to the colossal gravity that reigns here, which is nearly 200 billion times greater than what we know on Earth, if we could jump from a hypothetical stationary ship just 1 meter above the surface of the star, we would reach it in a microsecond. A microsecond would be enough to take us from 0 speed to about 7.2 million kilometers per hour. This hellish acceleration would cause a phenomenon known as spaghettification on our aching bodies, which is also well known near black holes. We arrive, and it's over, but let's take this death by vertical stretching lightly. Because this grim fate is nothing compared to what awaits us. Once the surface of the star is touched, well, landing is one thing, but leaving it is another. Due to the intense gravitational field, anything that falls onto the star will likely remain there forever. And the matter that once made us up will spend the rest of its non-life here. And you might think that nothing worse could happen to it. But that's without considering the fact that the star can attack the very nature of fire, your matter itself. Because the infernal conditions reigning here will, in just a few picoseconds, tear apart and strip your atoms of their electrons. It already happened during the descent, but it's occurring again. And to picture where the formless, nameless mush of degenerate matter plasma that was once you now ends up, take a good breath of imagination. According to theoretical models, the surface of such a body is covered by a thin, superfluid atmosphere, just a few centimeters thick at most, and whose dynamics are entirely controlled by the star's magnetic field. The only funny thing is that even if you could stand up, you can't. It would then be possible to literally walk on this atmosphere. with a density higher than that of diamond, and mainly composed of carbon-light atomic elements and iron. 56 and even more pleasant to breathe. The temperature of the mixture ranges between 100,000 and 1 million degrees. At the base of this atomic soup is a crystalline crust, mainly composed of iron-56 nuclei, with a temperature close to 10 million degrees. This crust, extremely hard and compact, is subjected, due to the atmosphere above it, to a pressure 10 times greater than that at the center of the Earth. And this crust can even, in exceptional cases, start to
crack. Hold on.
Here it can get rough. On certain neutron stars of a very particular type, called magnetars, stellar quakes have been detected. These occur when the combined forces of the star's rotation and its magnetic field cause it to deform slightly. The crust, which is extremely rigid, then readjusts itself by cracking violently during starquakes. This phenomenon was detected in 2004. When a magnetar located 50,000 light-years away from us was the scene of one of these surface quakes, which released in 1/10 of a second as much energy as our Sun does in 100,000 years. It is estimated that if this magnetar had been less than 10 light-years away from us, the cataclysm due to its intense gamma-ray emissions could have caused a new mass extinction on Earth. And here we are, in the front row, surviving, crust and all, on this thin shell where we think mountains can form. Yes, this episode reaches new heights of strangeness. For complaints, please refer to Nature. Although here, the extreme gravitational field eventually forms an almost perfect sphere over time. It is thought that at the beginning of the life of these stars, it is possible to find rare surface irregularities, on the order of a few millimeters in height, with a lateral spread of several kilometers. And it's amusing to think that the mass contained in the volume of these tiny features is much greater than that of our most imposing mountain ranges. And now, honestly, at this point where we are, we might as well get serious and start digging into the densest object in the known universe. And after going through a few dozen meters of ionized crystalline iron-56, 10,000 times denser than lead, we begin to tackle a kind of neutron liquid rich in highly radioactive isotopes in which circulate between, in the thin spaces, a gas of degenerate relativistic electrons circulates. Beyond that, after a few hundred meters of thickness, passing through a boiling mixture where the concentration of heavy atomic nuclei decreases with depth, we enter the inner crust. A kind of nuclear paste rearranged into a crystalline lattice, made up of exotic atomic nuclei abnormally rich in neutrons and immersed in a superfluid neutron sea. 100 billion times stronger than steel. And as we go deeper into this hell by the sheer force of imagination, the pressure here begins to turn matter into a superfluid of degenerate neutrons, mixed with a few protons, electrons, and other muons. And as we go further, matter becomes a strange mixture, sometimes called neutronium. With even more free neutrons, exotic particles begin to appear, such as mesons or hyperons. And we reach the outer edge of the core, knowing that it's probably much easier to eat your own head than to get in there. Yeah, it's technical, isn't it? Because in the heart of a neutron star lies the form of matter that is thought to be the most compact and solid in the universe. Here, the neutrons themselves may even break down into smaller elements and give rise to a quark-gluon plasma soup. It is there in the core that one of the best-kept secrets of the forces of nature lies, namely the secret of the final and stable state that matter can take in the universe. Everything is incredibly strange here. And although to be sure of what's there, we would have to be able to go there, we have models that describe it to us. A mysterious zone with exotic and still poorly understood physics where terribly violent and chaotic gravity quantum phenomena occur. And where a cubic meter of matter weighs more than the entire Atlantic Ocean. We have pretty much reached the point of density where it becomes strictly impossible to add anything more per unit of volume. At the atomic scale, there is no more room. Every tiny bit of available space is occupied. And only the neutron degeneracy pressure prevents the core of the star from collapsing in on itself. And that's where our adventure at the heart of the Death Stars comes to an end. Because if this strange compressed matter were to become any more compact here, it would be like giving birth to a singularity. By the way, maybe you'll find comfort in knowing that it's possible, for example, if a lot of people were to crash into this star, to make it exceed the Chandrasekhar mass, estimated at 3.2 times that of our Sun, and thus overcome the degeneracy pressure that prevents it from collapsing and, in the process, turn the neutron star into a black hole. This doesn't answer the question, what exactly do we find there? And what are we doing there? In any case, keep in mind that as extraordinary as they may sound to us Earthlings, neutron stars are not that rare. It's estimated that our galaxy alone could host as many as 1 billion of them, with about 200,000 being pulsars. By the way, it's pretty exciting to think that we've already found planetary systems orbiting around these stars. The very first exoplanets discovered in 1992 were found around a pulsar located about 2,300 light-years from Earth. And since that discovery, 2 other of these space monsters have been found to have planets.